an old, thank you. Dr. Uwe Bergmann is an old friend, and he has a long and distinguished CV, but you can look it up on the announcement for the talk. So rather than say that, just repeat that, I thought I'd just give a personal note. I first met Uwe just about 20 years ago when we started to work together on some of the problematic pages of the Archimedes Palimpsest, which is that picture, the third from the left, is very familiar to me. And so he's going to talk about, he has a wide variety of activity. And today he's just going to talk about the activity he does in cultural heritage, which is a small part, but it's certainly the part that brought us together. So I'd like to welcome Uwe.
Thank you. Is my microphone good? It is on. Thank you, Roger, and thank you everyone for coming. It's a great honor to speak in this Halls of Fame of Imaging. This is one of the places where imaging started, and today my talk will be mainly on imaging and a little bit on spectroscopy, but all of it will be on X-rays, and all of it will be on how the properties of X-rays actually combine spectroscopy with imaging in a way to gain information which otherwise is difficult to gain. And that's in a sense also how our work complements the work, the incredible work which Roger has been doing in the last 20 years. And that's also one of the reasons why we are still running into each other and work together. The big story, so now my frozen. No, we just try this.
You try
we have to try again. It's all frozen.
yeah,
Completely frozen.
Oh,
That's the Zoom part.
yeah, okay. Would we? The computer is frozen. Perhaps intended to disconnect it from the.
I don't think it has anything to do with it. I think that's.
Oh. Disconnected.
Okay, let's try again. It's still frozen. I mean, I can make this small. What is this? Okay. Oh, maybe that's because I didn't push that. Okay, let's try. Maybe that was the missing part.
Or maybe. Oh, maybe you will have to do it.
I don't think so. I think I should be able to do it. Okay,
Okay.
now it's
there
okay.
it works.
So now let's put that one back in. We will start. Okay, let's try. Okay.
Yeah.
Okay, we froze it. Thank you, Eduardo. So the story, our story started much earlier, but that was the headline on July 16, 1907, about the find in Constantinople, Istanbul, about writings of the great Archimedes. And Johann Ludwig Heiberg had discovered them in a prayer book in Constantinople. And he then realized there are, below those prayer book writings, there are Greek texts, which were copies of Archimedes. He ended up publishing the work, and it was a big success at the time. He didn't have modern imaging technology. He just had a candle, and he copied what he could see, and the book at the time thought was lost. But that's how our story started. Archimedes, of course, is a famous Greek mathematician who lived in the city-state of Syracuse, which is now part of Sicily. And amongst his many, many accomplishments, his most famous is probably the time when King Heroes asked him to estimate whether the crown which he had gotten from the goldsmith was made out of pure gold, or whether the goldsmith had mixed in some lesser noble metals to steal some of the gold. And Archimedes, according to the legend, Archimedes figured out the way how to do it is to determine the density. If we find the density, we can find out whether it's pure gold or not, because hardly any metal is as dense and heavy as gold. And he also realized it's very difficult to measure the volume of a reed because it's such a complicated volume. And it's easy to measure the mass, but it's very difficult to measure the volume. And that's what you need for the density. And so according to the legend, he had his eureka moment while taking a bath and watching the water of the bathtub rise from his uneven displacing body tipping into the water. And he was so excited that, according again to the legend, he ran naked through the streets of Syracuse shouting, "Eureka, I found it." That experiment could have been done like this. If you take a clump of gold and the same mass of a wreath, and you dip them simultaneously in water, if they have the same density, the upforce from the water, because it would be the same volume, would be the same, but if the density is different, one of them would rise. And according to the legend, indeed, that was happened. And of course, King Heroes was not happy that his crown was not made out of pure gold, and the goldsmith was on the run. Archimedes, the worst depiction I've ever seen of him jumping out of the bathtub is actually at the University of Manchester. I took the picture. It's terrible. They didn't even give him a beard. I mean, at least we have no idea how he looked like, but at least most of the depictions give him a beard. Some of them give him hair, some of them don't give him hair, but they even strip the beard. But it is an important moment, and I live in California, and our home state actually has on our seal of the state of California, Eureka. That is our motto of the state of California, and it's related to the fact that in 1849 was the gold rush, and gold was found in California, and of course our famous San Francisco 49ers with a golden helmet goes all back to Archimedes, to the Eureka moment of Archimedes. I went in Madison. When I joined Madison, we had usually a few dinners, etc. And I was sitting with the 5 mathematicians on the table, and I asked them the question. I said, I always heard Archimedes was one of the greatest mathematicians of all time. You guys are mathematicians. Is that actually true? And they looked at me and they said, Uwe, do you know what the Fields Medal is? I said, not so exactly, but I think it's the kind of most prestigious prize in mathematics, similar to the Nobel Prize, and it's only awarded not every year, and you have to be under 40 and all kinds of stuff. He said, yes. And then he said, have you seen one? I said, no, of course not. He said, look on the Fields Medal. So I looked on the Fields Medal, and here's Archimedes on the front of the Fields Medal. And then they said to me that I hope that settles your question. This was found by Heiberg. He had found 3 treatises of Archimedes, which had not been known until 1907. The stomach on floating bodies in the original Greek, it had been known, but only a Latin translation, and the Stomachion and the Method 2 treatises. And that's also one of the reasons why his discovery was so important and would make the front page of the New York Times. And then the book disappeared after World War I, when Constantinople was looted, and it was thought to be lost forever. And it resurfaced in the 90s in Paris, and it was auctioned off in 1998 at Christie's for $2 million. And the owner was contacted by our friend Will Knoll, to whom I dedicate today's lecture, and I'll say a few more words about him at the end. And he agreed to lend the manuscript to an integrated effort of conservation and imaging, and Roger has been at the heart of that integrated effort, in particular the imaging part of that effort. and has been done amazing work using multispectral imaging to uncover most of the pages better than Heiberg had ever seen them. But there were a few pages where even Roger's technique didn't work just because the physics of the page didn't allow the optical and UV imaging to bring out anything new. And this is an example, page 1 and 2, in terrible shape. You see a little bit of writing here. All of that is the writing of the monk. None of that is Archimedes' writing, which would be in vertical columns. And there were the 4 famous forgery pages. These were miniatures depicting the 4 evangelists and Luke and Mark, and underneath really important texts by Archimedes, and the bifolio also further mutilated St. Matthew and St. John. Multispectral imaging has been good for the backside, but for the front side, it was very difficult to get underneath those gold layers. And that's when I heard about it, was about 2003, and I had my own little eureka moment, and I thought that X-rays might help. And here is Superman. And of course, this is the real Superman, the true Superman. Röntgen, Wilhelm Conrad Röntgen, and his discovery changed the world. Today, we have about 40 billion X-rays taken every year. 4 billion. Half of the world's population, 4 billion, half of the world's population on average gets an X-ray per year. And I'm sure pretty much everyone in this room has gotten one. He should be on the Hall of Fame of the imaging because his work with X-rays was not in physics. It was all in medical imaging. I mean, the impact he had, the main impact early on was all in medical imaging. Right? I just want to point that out. He discovered X-ray on this cathode ray tube by chance, was told, because he had something in his drawer, it was illuminated. And then another miracle happened. He was able, after discovering a new form of rays, which he called X-rays, X for the unknown, he was able to convince his wife, Anna Bertha, to lend her hand for 50 minutes to shine these X-rays on her hand, so that he got his first, this very famous first X-ray image. And everyone talks about this X-ray image, of course. No one talks about how did he convince his wife to do that? I'm thinking, if I would have gone to my wife saying, sweetheart, I just discovered a new form of rays. I have no idea what it is. Let's call them X. Would you give me your hand to shine on? She would send me to hell. And she said, why don't I take your hand and I'll switch on? So dedication, devotion. That's all I have to say. Anna Bertha, she's a hero also. He was asked, what were you thinking during this discovery? He said, I wasn't thinking, I was investigating. Classical answer of an athlete. He was the first Nobel Prize in physics. And he wasn't even sure he should accept it because he had no idea what the Nobel Prize was. He didn't know whether there was anything important. And they said, yeah, you should just go, you will meet the king of Sweden. It's not a bad idea. I think he did the right choice. So we use spectroscopy. So here's a beautiful spectrum. This is the spectrum of sunlight. We use the spectrum of X-rays. Our X-rays, they can penetrate, and this is the theme for the whole talk. They can, you have in the center, this is a cartoon of an atom, you have the nucleus positively charged, you have all these electrons. If you have enough energy, if your photons are energetic enough, you can knock out these inner shell electrons. You cannot do that with visible light, or you cannot with UV light, barely do it, right? If you want to knock out these inner shell electrons, you need short wavelength X-rays. And when you do that, you generate a hole which is very short-lived, and then that hole is filled from an outer electron and sends out a second color X-ray. I call it color in the broad sense. Of course, it's not visible. And that is the X-ray fluorescence. And each atom, because each atom has a different number, each element has a different number of charges, like positive charges, and a different number of electrons, has its own characteristic X-ray spectrum. And here is such a spectrum. This is called the X-ray fluorescence spectrum. And we have phosphorus. You have energy and wavelengths going this way. There's phosphorus, there's chlorine, there is calcium. There are other elements. You see everywhere you see a peak. That can be iron, that can be copper, and that can even be a little bit zinc. And what we thought is, we knew that the Archimedes was written with an iron gall ink, the text, the underlying text and the top text. If we shine these X-rays and we knock out the 1s electron of iron, we will get a signal right here at the iron. So we can put our detector, we can put windows on our detector, like in a multispectral sense. You put a window on each detector, and so we can simultaneously track all these fluorescent signals while we scan our X-ray beam. Because the fluorescence goes in all directions, we cannot use a camera like a full-field camera. We have to use a very narrow beam and scan the beam, and then record for each pixel we illuminate, we record these channels, right? So the idea, oh, by the way, this one is also old. This method goes almost back 100 years. This was Nishina and Costa, a famous guy. They actually first reported that you can use the X-ray fluorescence spectrum as a chemical analysis tool, right? So this is, I mean, 30 years after Röntgen discovered X-rays. And, you know, by the way, the photo effect was only more than 10 years later, right? So Röntgen didn't really fundamentally understand what the underlying physics of X-rays, right? So a lot of the research, the 20s was when a lot of these things were really understood, when quantum mechanics also came about. And that's when they also realized how you can use these to get this X-ray fluorescence spectra. So for those of you a little bit interested in the history of this, so our approach was this: you use a powerful X-ray beam, you maybe use a slit to make it like collimated narrow beam size of a hair, 100 micron or so for 300 dpi, 40 micron for 600 dpi resolution, and we scan it across, and we record. At every point, we record quickly, in about 3 or 5 milliseconds, we record this X-ray spectrum. And then we put together a 2-dimensional plot for each of those X-ray channels, and then see what comes out. And if we put the iron plot, we will see every pixel where iron was involved. And that was the method which we used for Archimedes. And to do that, you need to get a powerful X-ray beam. You need a synchrotron facility. Here is an example. Synchrotrons typically have a linear accelerator, a booster which brings electrons at very high energies. They are then put in a storage ring. In the storage ring, these electrons, they go through wigglers and bending magnets, and they shine out these very bright and tunable. So the nice thing about synchrotron radiation, you can tune the X-rays with the monochromator. And you can have all these, there are up to 100 experiments in the bigger synchrotrons. You can have all these experiments at the same time. And it's a beautiful, powerful source for X-ray science. In fact, there is no source like synchrotron radiation for X-ray science. And that's the kind of source you really need if you want to get these images done fast. And that's the one we use. I just want to show you a few. So this is the European Synchrotron Radiation Facility in Grenoble. And you see the French Alps. This was the 68 Olympics happened in that area. I did my postdoc at this facility. This is the advanced photon size source in Argonne, outside Chicago. This is the largest synchrotron in Japan. The Spring 8 Super Photon Ring 8, 1.5 kilometer, built around a hill because Japan doesn't have much flat areas. So they built it really around like a holy mountain actually in the middle. In my opinion, one of the most beautiful by design is the Shanghai synchrotron. And this is the synchrotron with the most beautiful view in the world. This is the San Francisco and the Golden Gate Bridge in the background. This is the Lawrence Berkeley National Lab Advanced Photon Source. Each of the synchrotrons has specialized on a certain spectral range. Some are hard X-rays, the larger ones are harder X-rays, the smaller ones are softer X-rays. And they have a broad portfolio of science going on. If you want to be a scientist and be exposed to a lot, go to a synchrotron, you will see a breadth of science going on there all the time, which is really phenomenal. This is the oldest synchrotron, you might know this one. first one, you can see some hard X-ray beamlines with Hutchins and some soft X-ray beamlines here. Do you know this one? Who knows this one? Apple Building, right? It's not a synchrotron. It's actually not too far from the Stanford synchrotron, but it's not a synchrotron, but it sure looks like a synchrotron to me. This is the Stanford synchrotron light. So that's where we did all the experiments on the Archimedes Palimpsest. Here's Abigail Quant, 20 years ago, putting in the first test page of Archimedes. And this was basically in the second beam time in 2006, we had this really big breakthrough. This is folio 1 of the Archimedes Palimpsest. This is the iron X-ray fluorescence image. And when this image came out, and all the horizontal writings are the writings, Archimedes writings, the final parts of the treatise on floating bodies in Greek. No one has ever seen those in modern times. And Reviel Netz, the scholar from Stanford, came down and he was amazed. And he took these images and he wrote an email. Here you see Roger is copied. Roger is on the thing. Nigel Wilson is copied. Will Knoll. And he sent it to Keith Knox, who was doing the image analysis. He said, XRF is sensational. I attached a transcript. Previously, I squeezed out 3.5 lines, noting a couple of errors, and now I can read it all very easily. So that was a big success. We had also pretty big success on some of the other pages with the where we had those scriptures, which were basically those forgery pages, and those were also extremely successful. We also, at the corner of this page was the colophon, which is the dedication by the Byzantine monk who actually wrote this prayer book. It's not Archimedes, but it's the guy who actually did the palimpsest, who's created it off. And this is the X-ray fluorescence image. And you can see it is really beautiful, and you can read for the first time, you can read what he said. He said, this was written by the presbyter Johannes Myronas on the 14th day of the month of April, a Saturday of the year 6737. Byzantine calendar starts with the creation of the universe. So 6737 years. In our calendar, it's the year 1229. And the 14th day of the month of April was the Saturday before Easter Sunday. And we think that he was just scrambling to get his prayer book ready for the Easter Sunday sermon. And it took almost to the day 777 years to read actually what Myronas had erased and uncovered in the Archimedes project. And ever since, we have been contacted and reached out to other projects using that approach. We have now perfected the method. You can go to SSRL and use it and write proposals. And I'm going to share some of the work which we have been doing since this great project. It was a lot of it was summarized in these 2 books. Roger is in there, of course, as well. And I just wanted to quote our friend Will. He also wrote a great book called the Archimedes Codex together with Reviel. Wonderful read. And here's what he wrote about when he first saw the setup at Slack, which I really was responsible for. So let's read this one. It didn't look like a professional setup. Inside the hutch, the guts of the machinery were scattered all over the place. Outside the hutch looked like an electronics junkyard. Not very flattering. And then he continued, but I soon realized that was precisely what this professional operation looked like, because looks don't matter, and essentially new machines were tailor-made for different operations every day in this extraordinary place. We kind of saved it in the second half of that. We miss Will really very, very much. He's such a great, he was an incredible guy and really instrumental for this. We were approached by a student from Germany who was trying to do a full transcript of Cherubini's famous opera Medea. And Cherubini had erased it himself, and he used probably shoe polish to erase some parts of one of the areas in this opera. And we used XRF to actually bring out the music. And we were honored by a postcard to the 250th anniversary of Cherubini. And this is the full transcription by Heiko Kuhlmann. He was the student. And most importantly, if you now look at the air, and if you go, I have a YouTube here for you, if anyone wants to watch it later. Now when they perform the opera, the X-ray imaged part of this area is included. So it's basically this section here of the opera, which had been missing, and it's now included from the opera because of X-ray imaging. So we have made this long opera even a little bit longer. Our friends from Silicon Valley, Bruce and Sandra, gave a gift to Stanford a few years ago, 2017 or so, and we have now a new setup with a very professional, no longer electronic junkyard, professional scanner, improved detectors. Here you can see a 4-element detector, state of the art. We have different pinholes. We can change the size, the beam size very quickly. We want better or slower, less resolution. And most importantly, we are now going from multispectral X-ray fluorescence to hyperspectral X-ray fluorescence. We measure now for each pixel the whole 2048 channels of the readout. And we can then later post-process the data and see whether they have overlapping XRF signals to subtract out the signal and get like higher quality of elemental maps in the future. This was all done due to this gracious gift. And we did a few. I just show you this one briefly. This is the Galen Palimpsest. Galen was a very influential physician, and he was also, I mean, if you look at we talk a lot about interdisciplinary today, right? And then some people even said, oh, we are struggling with getting funding for interdisciplinary research, etc. Look at this guy. His scientific discipline, including anatomy, physiology, pathology, pharmacology, neurology, as well as philosophy and logic. To me, that's interdisciplinary research, right? They found this catalog in the St. Catherine's Monastery, and Syriac is basically, it's an interesting language. It was the language that was spoken at the time of Jesus also, and it was like a transition. It was not an Arabic language, but it was also not, Greek or Roman. So it was at this transition, and so it's an interesting to have a treatise by a famous Greek physician translated into Syriac shows you how this information has spread to the East during that time, and of that was of interest. And here is Mike Toth. We are doing some handheld XRF to make sure that this is really iron gall ink. And here we have the conservators from Stanford, Kristen St. John, David Brooke, and Michelle Smith. They looked at the book because they actually responded. I'll show you a little video how they did it. So this is Michelle Smith talking.
Had to come here to be disbound so that it could the leaves could be removed from the book so they could be prepared for disbound the book by flipping the threads and taking out the quires, the folded pieces of parchment, looking at each leaf, recording any damage that I saw, photographing and putting boxes and took them to Slack. And then I trained all the scientists who would be handling the leaves so that they would know how to handle them safely and prevent any damage.
So here you see that like how we basically shows from a book. And by the way, the Archimedes Palimpsest was originally also this one for, I think, for multispectral in a very similar way. This work is only possible in a big collaboration, and you have to have experts from all fields, including conservation scientists, who are very careful with the treatment of all these artifacts. Here's a little video. So this is Nick Edwards. He's a staff scientist at FLAC, and this is Mike. And here you show, so basically, we usually image it from both sides because we have 4 layers of text. So here you see him turn it around. It's very easy. It takes literally less than a minute. You can clip it on, and then you leave the hutch, for radiation safety, and then you scan it. And here you can see the scanning, and you can see on the screen. You can follow on the computer screen. We have a program now. You can watch each channel, everything you're interested in. You can see it and depict it as it's scanning, and see whether the experiment is working well or not. It really has come a long time. The text we were interested in is this one, very weak. You can see just a tiny bit of it. All this is modern text, which is more, top text, which is not of interest, and we struggled with that. We just looked at the iron image first. So let me show you. So this is the visible light image of this palimpsest, and I think there was also multispectral imaging done. Yep. I know that. This is the multispectral image. This is the iron map, where we hoped to see the best writings. And you can see that there is stuff here. You can see it. But our scholar who was at the beamline with us, Peter Porman from Manchester, wasn't happy. He said, I cannot read it. I cannot read it. One of our scholars is an expert in machine learning in advanced algorithms. He said, give me those. Tell me areas with text, tell me areas without text, tell me areas with overwritten text. I would train my program, let's see whether we can improve it. And he did. And this is the outcome. We have now exposed these pages to this machine learning algorithm, and we were then able to actually finally read it. And we did about 50 of those pages. It was mass production. We had 2 beamlines running simultaneously at SSRL. I'm not sure that has ever happened at the synchrotron, where we just morning to night scan all these pages. And this publication is coming out soon, but that has been a big success. The current project is called From Jigsaw to Gutenberg. We all know Gutenberg, or we all think we know that Gutenberg invented the printing press, movable type. It ushered in the Renaissance. It was one of the biggest revolutions in humankind in the first or in the second millennium. And it has really changed our age of information. But he didn't invent it. The Koreans had already movable type printing before Gutenberg. And the most famous is Jigsaw. It's a document called Jigsaw, and there are other early Korean documents. The Korean ones never took off to the level of Gutenberg. And that's probably also one reason why, particularly in the West, we are not as informed. The Koreans are very proud of that, and we should all be very proud of that. In fact, it's such a big deal that Jigsaw is at the BNF, Bibliothèque Nationale de France, and when the Koreans decided to build a high-speed train in Korea, they told they were debating between the German IC and the French TGV, and they said, if you give us back the Jigsaw, we'll take the TGV. And the French said, we are not going to give you the Jigsaw, but you'll still take the TGV. And they did that. They still took the TGV. For whatever reason, I don't know. I think the German is better. Anyway, the point is, it's a very high level of contention, and we are trying to shed light with X-ray fluorescence on the origins of printing. And we were able to secure an original first edition Gutenberg Bible printed and a pre-Gutenberg Korean printed text. And other leaves. So these are the 2 stars, those 2. A Gutenberg Bible, private owner, by the way, same owner as the owner of the Archimedes Palimpsest, just for Roger's information. And these are a replica, and then these are also other Korean texts, and then we had also many Western leaves, which are just a little bit after Gutenberg. Setup, very similar. Here is the Korean, Confucius. Here is the Gutenberg Bible. And here are some results. This is an optical image, and you see, for example, big copper signal, mercury on those red ones, not surprisingly, calcium, like a little fold. You can see that here, a little tear shows up. We were surprised how much metals are in these inks, because these were none of them was an iron gold ink. They were carbon inks, either oil or oil in case of Gutenberg, or water in the case of the Korean ones. And here you see a little bit more. So Confucius had a little bit iron, no iron in the Gutenberg, tons of copper, tons of lead, a little bit lead here, and a lot of copper here. So we started to learn more about these inks, and we said, you know what, we need to do a test because we are not sure where these metals come from. So we started to do our own printing test. Before that, we did a woodblock print, which was supposedly with the same ink as the ones which we measured, as the metal type print. And woodblock print, nothing. No metals in the ink, empty. Anyone, copper, iron, nickel, zinc, you could look at any metal, there were no metals. And so we started to replicate early Western prints by making like an alloy of lead, tin, and antimony by Peter Barrett. And we basically, Jennifer Jakai and Minhal, they made some ink according to the old recipe. And then we basically inked those things and we printed. And we did one normal print, one ink spread without printing it, just spread the same ink on the paper, and one blind print where we only printed, we only pushed the metal into the paper, but no ink on it. And we looked at the XRF. And what we found is that even on the blind print, you already have lead coming out. And if you ink it, the spread ink has basically very little. This is the signal, the gray is the signal of the spreading, very little. But if you ink it, the lead shoots up. So no question that in the printing process, lead is leaching out into the paper. And the same is true for some of the other metals. Similar, more recent experiment with copper leaching in bronze. So this was a replicated Korean type. And here again, lead is leaching, huge copper leaching, right? So blind press already, blind press very little, but once you ink these metal types, some of the metals leach into the paper. So that's where we are right now. We now know that all these early prints that we have, which are in existence, are basically a preserved time capsule of the types which were used when they were printed. We know that we see, if we see metals in those things, we know we have a very good idea of what was used. No one at this point knows what Gutenberg used. It is not known what alloy he used. There's still controversial information, and with this work, we are going to shed light on what was used in these early. We know much more about the early Korean prints, and we also mentioned actually some of the early prints. Minhal is my student, and she did a lot of this work. And here is the group from the Jigchi to Gutenberg. Randy is leading actually this overall effort. And we have our colleagues from Korea. We have our colleagues from the Stanford Library, Jennifer, who has been since the Archimedes project with us. Roger knows her very well. And then we have Stan Nelson and others. And these are the two scientists from SSR. And of course, here's Mike and his nephew, Henry. They both came to the beam time, and this was still during COVID. So they were wearing a mask. This work on XRF has inspired a whole different field of research, which I hadn't thought about, and I'm going to talk about that right now. So here you see a beautiful soaring vulture, and you have seabirds, you have hummingbirds, you can have silent owl, you can have the fastest animal on the planet, peregrine falcon. You can have one of the fastest land animals. You can have agile swimmers on the South Pole. You have some of them catch in midair, or they can catch out of the water. They can catch underwater. They can fly. They can climb the Himalayas in a single day. From India, from sea level, in one day, they climb up 25,000 feet. Bar-headed goose, world-class athlete. They are incredible divers and have beautiful colors like this pink, or these colors, or of course the parrots, or this one, a beautiful peacock. And they have one thing in common, which distinguishes them from most other animals. First of all, they have spread throughout the whole Earth, and they are about almost 10,000 species. And the one thing they have all in common towards any other animal is they have feathers, and they are birds. But before modern birds evolved, almost 100 million years earlier, was a creature roamed the earth, which was a primordial bird. Maybe the first bird, the original bird. The German name is Urvogel, which stands for original or primordial. The story about this incredible animal started in 1861 on August 15. And Hermann von Meyer, he reports from the lithographic shale in Solnhofen, Bavaria, about a slab and counter slab of a fossil with which great clarity can be evidenced as a feather that is not distinguishable from bird feathers. And he says, in the known organization of pterodactyls, there is nothing known that could be concluded as a plumage. This would therefore be the remains of a bird of the pre-tertiary. So this was late Jurassic. Didn't have at the time, they didn't have the dating with millions of years, but they knew that there shouldn't be birds in the Solnhofen limestone. This is much, much older. It was so controversial. By the way, this paper is very, very famous publication at the time, similar to Nature today. It was so controversial that some people even argued that it can't be right. You must have maybe it's a leaf. It wasn't a leaf. Look at this. This was the fossil. This is a modern blackbird feather. 6 weeks later, von Meyer dropped another bomb in the scientific literature. This is September 30. So the other one is August 15. Following my letter on August 15, I can now report that I have studied the feather and it came in complete agreement with the bird feather. At the same time, I've received news that an almost complete skeleton of an animal covered with feathers was found. All of a sudden, he doesn't call it a bird anymore. He says an animal covered with feathers. Compared to living birds, it shows some differences. I will publish the feather that I studied with exact drawing. For the description of the animal, I suggest the name Archaeopteryx lithographica. Archaea, ancient, pteryx, feather. What made this find so significant at the time and still today is the fact that it was a transitional fossil. It had signatures which looked like a modern bird feather, but it had other aspects which looked completely different. They didn't look like a dinosaur, but they also didn't look like a bird. And I'll show you in a second. And of course, the origin of species had come out just 2 years early. And there was a lot of criticism on Darwin and said, show us, you cannot be right. Your theory cannot be right, because otherwise we would find fossils of all kinds of animals which we have never seen. And of course, they dismissed the fact that most animals die and we'll never find anything of them. But here was this transitional fossil, which was clearly it didn't look like a bird, but it also didn't look like a dinosaur. So it was, in that sense, it had also a big historical significance. This was the time of when Archaeopteryx lived. The Bavarian foothills of the Alps used to be a tropical archipelago. And it took me a while to realize, how is that possible? I mean, it's Bavaria, it's nice, but it's certainly not tropical. It's cold in the winter, you can ski there. And this is why, because the Earth actually changed over the last 150 million years, right? So this is an animation. And here's a picture. 150 million years ago, Africa and South America were still connected. The Alps hadn't formed yet. And where today is Central Europe was a tropical archipelago. Keep that in mind when we find fossils, and we, in particular, really old ones, we assign them. Look back, how was the Earth at the time when those animals lived there? It was a completely different place like they live today. Look at, it looks nothing like our Earth lives today. Here is a comparison. This is a rooster with a modern bird. This is Archaeopteryx, still T. And this is Bamviraptor, which is kind of the small one in Jurassic Park, which is chasing the scientists around the kitchen. So this is Archaeopteryx, and I could spend a lot of time to go into detail, but it doesn't look like a dinosaur, and it also doesn't look like a chicken. We now know Archaeopteryx was actually a dead end in the evolutionary sense, but there were other fossils, similar ones, mostly from China, Liaoning region, which are kind of the real ancestors of our modern. But it was important. There are only about 13 specimens of Archaeopteryx. It's one of the most sought after fossils in the world. I show you a few of this. This was the London Archaeopteryx, the first one. This was the feather I mentioned. And one of the best preserved is the Thermopolis Archaeopteryx, which is here. And my good friend Peter Larsen, who is a fossil hunter, he heard about the Archimedes project on NPR. He contacted one of our colleagues, Bob Morton, because he wanted to contact us, and he knew Bob. And he basically started, we started this research because he contacted us after hearing about the XRF. And he said, maybe we can learn something about Archaeopteryx. And here I was visiting recently, I was visiting him. He's the owner of the Black Hills Institute, which has tons of beautiful dinosaurs. This is Stan. And by the way, Peter Larsen is famous. He discovered the T-Rex zoo. And there's even a documentary about him on CNN called Dinosaur 13, if you ever want to see it. He got into legal problems and all kinds of stuff. And I know him very well. I don't say that just to impress you or something, but they basically screwed him. And if you look at the documentary, you find out. But he's doing very well. He's fine. He's happy. And here you can see him. That's just a few years ago. Here he is bringing the Thermopolis Archaeopteryx into the beamline, same beamline where we did Archimedes. We had like a thin window around because we wanted to measure some of the softer X-rays also. So we put the whole fossil under helium and put the detector very close. And we were able to find, do elemental maps. Here you have my two good friends and colleagues from Manchester, Roy Burgelius and Phil Manning, both are professors at Manchester. It's like finalizing some of the samples at the Hutch. And here is a picture of Thermopolis Archaeopteryx. And we were focusing on this area, which has the feathers, where we thought there's really no chemistry left, just some imprints. But we did find, in fact, there is some original chemistry left. This is the optical image. And this came out when we looked at the XRF phosphorus image. And we could see the feather shaft, the original 150 million year old feather shaft of Archaeopteryx. The phosphorus of those feather shafts is still preserved in this fossil. And we found sulfur as well. And we found something about the metals as well. Here you have an image. And we also found that they had restored some of the bones. For example, here they had restored this one. Look, here you think it's like a norm, but this was restored. This doesn't have any phosphorus. And this was restored as well. And there were even some we saw some fingerprints in the chlorine thing. People have like that. Incredible sensitivity of X-ray fluorescence. That's another thing which I want to stress over. XRF is very, very sensitive. If you ever want a forensic tool and you want to find some traces of some element, use XRF. It'll help you. We then got from Berlin, we got the Berlin feather. And we also measured that one. And here we used a technique called X-ray absorption spectroscopy, which means that when you knock out an electron, you can actually learn about the chemical speciation depending on where you can put this electron. In the empty state where you can put this electron, there are resonances. And these resonances, just before you can really put it out, they tell you about the chemical species of this element. For example, you have thiol, sulfoxide, sulfonates, sulfate. They all have a different signal. So what we decided is let's measure on the organic sulfur and on the sulfate and do an XRF scan with the excitation on those resonances, right? So it's not just an element XRF scan, but it's a chemical XRF scan. So you're adding a little bit more spectroscopy to it. And here you see the results. This is the visible light of the feather. Here you have the copper. You see a little bit higher copper here. Here you have the nickel, a little bit higher nickel here. And then the organic sulfur, you see more signal here in this corner, and the inorganic, the sulfate, has really no correlation, right? Because that was not from the pigments. We had this hypothesis that the sulfur, there should be signature of the pigments in this fossil, and these ones we think these were little parts which might have been part of the feather shaft, but something which was not in the organic form. And by looking at this, we were able to basically reconstruct the shading of the Archaeopteryx feathers. So we believe Archaeopteryx had feathers in terms of their pigments, which were kind of shaded like. And here you see part of the group who were looking at the images as they come up. Victoria, Roy, Diana from Berlin, Bill Sellers, and beamline scientist Roberto Alonso. Now, some elements, so I'm coming to the last part now. Some elements are hard to do with X-ray. Okay? So, in general, some elements are hard to do with X-ray because they're so low in the periodic table that the resonances and the X-ray emission is very soft. We call it very soft X-rays. They do not penetrate. They do not penetrate very well. So you have to do all the experiment in a high vacuum. And even if you do them in a high vacuum, all you see is the surface of the sample. You don't really see into the sample at all. So these first row elements, carbon, nitrogen, oxygen, etc., lithium, beryllium, all of those cannot be easily done on, let's say, an archaeological or a paleontological sample. Because what you would see is a signature of the surface and not really of the bulk, what you're interested in. But there is a way out. There is a trick. The trick is, and this was work I had been doing even before the Archimedes Palimpsest, that you can use a phenomenon rather than absorbing the photon to knock out the electron. You say, I'm going to scatter the photon, and I only take part of its energy, and I measure the energy difference of photon in, photon out, and that energy difference corresponds then to the binding energy, what normally would be the absorption. In that sense, you can measure resonances which are very low in energy because the energy difference, small energy difference is fine as long as both X-ray in and X-ray out is still hard X-ray. You can measure that. And it's called X-ray Raman spectroscopy. Raman, because the Raman shift is somewhat related. In the Raman, you measure also a shift in frequency in the case of Raman from a vibration, here in the case of an electronic excitation. Carbon is very interesting because carbon, of course, has an incredibly rich chemistry. And if you can do carbon, you can access a lot. And here is an example of the rich chemistry of carbon. This is pure carbon graphite. This is pure carbon diamond, totally different. Completely different properties and completely different density and everything. And there are millions of carbon compounds in the world, literally millions, with very unique properties. I mean, our skeletons, we are largely made out of carbon, right? And of course, we have water and many other things, but carbon is really which holds us together. So this is the idea. Inelastic scattering. So rather than absorption, you give a little bit, you scatter and give a little bit. What makes this technique difficult? The one reason why this technique is difficult is the cross-section of this inelastic scattering is small. But there's another reason. It's very difficult to measure X-rays which go in all directions out, like these inelastically scattered X-rays with high energy resolution, with high spectral resolution. It's very difficult. You need to have a spectrometer. A detector is not going to cut it. You need to have a spectrometer which has very high resolution. And so we built one of those spectrometers. This is one of the largest in solid angle. These are 40 silicon crystals. Each of them is curved and it's even diced into small cubes. Each of them has about 10,000 cubes. You don't see that in the low resolution image. And with this, we can collect this large solid angle, and we only collect exactly one energy, plus minus 0.3 eV, like very high resolution. So if we scan the incident photon energy and we measure the scattered photon energy, we can scan through the absorption edge, and we can get carbon spectra, but not using soft X-rays, but using penetrating hard X. That's the idea behind this X-ray Raman scattering. And we showed that. So these were some samples in asphaltenes and heavy oils. You can see these are different carbon compounds, right? And you can see each of them has a very different absorption spectrum. And there's a library of thousands of such spectra. You give me an absorption spectrum of carbon, I can find you in the literature, the resonances, and I can find you the carbon types of carbon which are in that sample. So very powerful for carbon. And one of the really beautiful experiments was done by my current postdoc, Rafaela, and colleagues, and I was part of this work as well, where there was an amber, 50 million year old fossilized ant inside amber, all carbon. The ant was carbon and the amber was carbon, but they had different carbon because the ant had chitin and elements which are not in the amber. And so by using this difference in the absorption spectrum, in the carbon spectrum, we were able to get actually a three-dimensional picture of that fossilized ant inside this amber 50. So here I want to show you this is more recent. So Loïc Bertrand, he's a good friend and colleague of mine from Saclay, and this is Rafaela. And then we've teamed up with Rachel Popelka-Filkop, who is a professor at Melbourne, and she has access to a collection of rare Australian plant exudates. So plant exudates are resins. This is the stuff of when you cut a tree, the sap which comes out. In fact, since we are in the country of getting your maple syrup, right? In a sense, maple syrup is related to that. It's just much more liquidy. But trees have this reaction. Here is a Santoria, and you can see this. You can see these really sticky stuff. You touch it, it will stick to you. And sometimes when the trees get hot, they actually burn and fall to the top. These materials have been used for tens of thousands of years by Aboriginal Australian artists, and also for materials for all kinds of uses. And we had access. So here's one of these artists, Christopher Pesey, like contemporary artist. This is a famous painting used with resins, natural resins from Australian trees to make the paint for this artist. And here's a little bit more detail. And there's a beautiful book which describes and how this painting with this kind of materials also connects him to nature. Another famous one is Robert Thomas. And this is one of his artworks. Some of you might be familiar with that art. Again, this is all based on those natural resins out of trees. And we were lucky, so here's another detail. We were lucky to get our hands on a collection, and an old collection. I'm not going to go through the details, but it's an old collection which was collected from 1876 to 1905. Very well preserved, documented. We have about 60 different of those old resins, and we have used this technique, this X-ray absorption spectroscopy technique, to characterize those resins. And here is an example of different components which are in Santoria, and in those these are all the ones which in Santoria and in those different components. Here you see carbon spectra, and I don't want to go too much into detail. I just want to show you that each of those carbon spectra you can fit with all these different peaks, and then by doing the ratio of those peaks, you can tell what are the carbon chemistry in those peaks. And my student now, so this was published 2 years ago, and my student now has been able to get all these new spectra. And she is now building a tree, almost like a tree, what you see when you look at paleontology. From these carbon spectra, she's now building a tree, how all these different carbon resins are related to each other from the analysis. And she's using principal component analysis. And of course, in the future, we are thinking maybe we eventually can also do some machine learning analysis to disentangle the carbon chemistry of these Australians. This is Sophie, this is Rachel, this is Rafaela. and Minhal also had in one of those experiments. And I want to now, I'm finished with my talk, and I want just to show you, make one little advertisement. This is a paper we published a few years ago, and it's a long, 70-page long. If you want to take a picture, or if you want to get the, it's a review paper in a book, and it describes all this research in cultural heritage, which I've been doing in the last 20 years, thanks to Roger's friendship and collaboration also. It's a little bit hard to get because it's in a book, but of course you can go also to my homepage. You'll find it on my group homepage as well. And we have many collaborators, right? Here's the whole group from the Archimedes project, from the fossil imaging. I cannot go through all the names, but I do want to show a few pictures of the old days. So these were some of the pictures, Abigail, and then here's Will Knoll. So I'm going quickly through them. This is also not super high resolution. This was Will, and tragically, our friend Will died earlier this year from a car accident in Edinburgh. And actually, he was hit by a truck or by a van. And he was the one who immediately replied when I contacted the Wallace Art Museum 20 years ago. And he was such a supporter and enthusiast about this work on the Archimedes project. He led the project brilliantly, bringing together all these different characters with different egos. And he always told us, Archie, if in doubt, Archie comes first. Archie was the nickname for the Archimedes Palimpsest. If you have ever any disputes amongst each other, who is in the press, who is not in the press, always think Archie comes first. That was one of the most important things he told us. Here's a beautiful picture. And I asked Roger to, here's Roger. This is 20 years ago, guys. Abigail Quant, Keith Knox, Mike Toll, then Bob with his whole family. This is Bob Morton. Bill Christensberry, you might know him. And here is Will with his hat. And Roger, tell me again, why did you have this Indian outfit?
Keith and I, and Dale and I had just come back from India, and Will wanted one of those outfits, so we bought a whole bunch of them.
Okay.
We had pictures going out to dinner.
I think that's a good enough reason. Here you have him again. This is Jennifer. We had dinner, and here's Roger, and we recently at the memorial service in Princeton, we took this picture, and there's the same group like 20 years later, and look at who is in the background, looking at us from the top. Will Knoll on the painting in Princeton. But this is photographed in, and I want to thank you for your attention, and I want to dedicate this lecture to the rocket man Will Knoll, and I want to thank you also for your
We have questions.
You talked about the thought process for a given project in balancing the scan rate to total resolution needed by essentially the end people.
Yeah.
Try to deal with whatever you can produce. How do you get to a decision?
Excellent. That's an important and excellent question. Why is it so important? Is because if you double the resolution in each direction, it's already 4 times longer because it's with a square, and because your number of photons is reduced. If you have already maxed out your synchrotron, you lose another factor of 4. So you lose a factor of 16. In some cases, you lose a factor of 16 just by going from 300 dpi to 600 dpi. And so the answer is the scholars tell us what they need. The scholars tell us if the resolution is good enough. And also we look, of course, at the size of the letters. Archimedes we did with 600 dpi. Ever since, we have used about 300 dpi, and that has been fine. Archimedes was particularly small. We did a Quran palimpsest. We did also the one in I think for the opera I think we might have also done 600, but most of them we actually use about 300 dpi, and that helps a lot with the scanning time. Our scanning time is currently, we can do faster. We do about 3 milliseconds per pixel. So you can do the math how long it takes. Like for a megapixel, for a megapixel image. And we were limited in the past by detector speed. We couldn't use the full intensity. Now, these new readout electronics and the better detectors, now we are limited eventually by the mechanical speed of how fast you want to scan those, because you have to slow down a little bit, step up. And then there's the question is, at what point does it make sense to scan even faster? But I would say, yeah, a few hours, like a full decent sized page with 300 dpi it takes a few hours. Can you do faster? Maybe if you could come up with optics where the optics scans the X-ray beam, very difficult to do. We thought about it because X-ray optics is not like laser optics where you can have mirrors easily. So you need to have it more complicated. But I think that the biggest advance from 20 years ago to now has been better detectors and also the fact that we take the whole hyperspectrum and that we have now analysis tools, including machine learning, to get the best image quality. I would say that has been the biggest improvement since the day when we started. Yeah. Yes. So one, and then I see.
Wisconsin, California.
Sorry?
Do you see you live in Wisconsin or California?
I live in both places. Yeah. So when I teach, I'm always in Wisconsin. I have my lab in Wisconsin. We have an XUV femtosecond laser lab there. And I also, our home, like my wife, is close to Slack where we live. So I just came from California, but I also spend actually a lot of time in Madison. I think it's about perfect. But anyone has anyone been there? It's a great place.
Yeah, I just got back.
Yeah. I really like the farm. It's really fun. It's about similar size to Rochester. And I think the campus is maybe also comparable. I don't know exactly the size, but go ahead.
Just bombarding these pages with X-rays that the pages or the game or anything like that.
Yes, that was a big concern early on. And maybe, Roger, you remember, I mean, obviously no owner of any important, and also with the fossils, by the way. With the fossils, I was more worried about if we drop it. What is it about data break, right? And this that archaeoptics was officially listed at $6 million, right? And you don't want to. I mean, I actually didn't even want to put it in the beam. I let Pete do it. They came by. They didn't fly. They came by truck from Wyoming. They dropped it. So we did some tests. We went to Argonne, which has the brightest beamline, and we put parchment in, and we exposed it to X-ray, and we looked at what happens. And we even sent this result. First of all, we could start to see decoloration. It looks like almost like you're burning it, so it gets brown. And we also send the papers at lower doses to. Do you remember the guy in Ottawa? We had a conservation scientist who worked with us. He looked, because he was the conservation scientist was concerned by when we ship these parchment pages to Slack, for example, or anywhere else, and the humidity changes, what happens because they start to curl up and things like that. So he was always worried about that. But in fact, we had to air condition our hutch. We came up with our own humidity system in the hutch while we were running the Archimedes experiments, because these lab environments are usually pretty dry. And parchment wants to have around 50% humidity. And so we know very well what dose we could give it. And I can tell you the dose we gave it was at least 100 times less than the dose where any changes were seen. It's such a short exposure, right? So 2 milliseconds, it's such a short exposure that we did not expect, and we did not see any damage. Now, when you do spectroscopy, like we did, in some cases we need to measure absorption edge, you have to stay longer. And there you have to be, there you have to be even a little bit more careful, right? For the rapid scanning, those had never been.
Just another quick question. With the X-ray, especially with the Gutenberg Bible and things like that, can it tell you information about not just the information as well? Like, can you do some kind of dating based on?
Oh, for the paper, you mean?
Yeah, for the paper.
I mean, there are better methods for dating, right? So, I mean, of course, they're destructive, but dating, I mean, I don't think on paper and parchment, nothing beats carbon dating.
Right.
But you can find, for example, different papers were made with different materials over the years. And if you have good information about that, you can learn something about the provenance of let's say a parchment by just looking at the different components. We haven't, to be honest, we haven't really done it. I think Abigail eventually found out whether Archimedes was goat or sheepskin. I think, right? But she didn't use the X-rays to do that. She had some other analytical chemistry methods to actually do that assignment. But it is a good point. And I want to point out the inks. So we had one project on the palimpsest also, where it turned out that the two inks, the top and the bottom ink, had different levels of zinc. They both had high levels of iron, but we were lucky that the bottom ink, which we were interested in, had zinc and the top ink didn't. So the best XRF image was not the iron image, was the zinc image, because it basically took away the whole top layer and you could just see the overwritten text. So composition, metal compositions in those inks, they vary a lot between different inks, and so that can sometimes. And then you had a question.
Big talk. I had two questions. The first question was this, the dose. And the second question I had is that do people use instead of X-rays, electron beams to study these manuscripts? Because something like a yields spectrometer, that would do exactly what you are doing with XRF.
So people have, there is this, basically you can get X-ray fluorescence from electrons. You can bombard your beam with electrons and then get X-ray fluorescence. That's one. Let's talk about yields in a second. So the electron method has been used, but usually for much larger objects, because you don't get good spatial resolution with electron beams. And also they have been used for objects where you need much deeper penetration. So where you basically, yeah, I don't remember what exactly they use. So X-rays have the advantage that the X-ray optics, in particular with synchrotron, is just outstanding. You can now get X-ray beams with 50 nanometer size. And I want to let also all the students and everyone who asked the question, what makes X-rays so special? We always think the penetration, right? But I can tell you one thing, more than the penetration is the fact that at a short wavelength, you don't have refraction. The index of refraction for X-rays is essentially 1. It's 1 minus 10 to the minus 5 to 10 to the minus 7. For optical light, I can shine, I can take a flashlight and look through my hand. I can see the red on the other side. I will not see any bone because the information from the light is completely lost, because the light bounces all over the place from 1.5, 1.3 index of refraction for X-rays. They just go straight through, almost, not exactly, but almost straight through. And so that's important. The short wavelength makes, you can have better optics, you can get higher resolution. An X-ray microscope has always higher resolution than an optical microscope. And the third aspect is this element specificity by knocking out electrons of different types. So, but the penetration and also this lack of refraction is really important for it, right? And so going to the electrons, yields. By the way, what X-ray Raman is exactly the same as yield, except yield is done with electrons. So it's electron loss spectroscopy, and you need an electron microscope for that, right? And so these electrons, and the electrons at the energy of yield, again, strongly interacting, you will mainly see effects of the surface. So if you want to have a bulk probe, if you want to get deep in, the yields method is not right. And of course, you guys probably know there are other methods. That FTIR is powerful. Raman, optical Raman, NMR, right? And in fact, my student Sophie on this Australian planet, she has done the FTIR on all the samples, and she has done the NMR, and she's now going to Melbourne next year, where she does mass spectrometry. Mass spectrometry can also be very important by figuring out chemical compositions of chemical elements, right? So ideally, we want to throw all of them. Often, some of them are destructive, or many of them are destructive, and few of them you can do as fast, right? With getting as fast 2D spatial information at XRF. Of course, multispectral is even much faster, right? But that doesn't have that chemical. So always keep all of them in mind, right? When you think about any of them. Really important.
Do you get any isotopic information?
Not from the XRF. Yeah, MESPAR. So MESPAR effect is a way which is sensitive to the isotope, but no, the XRF is not, that doesn't have a sensitivity to the isotope. Okay, good. Well, thanks everyone.
If anyone is interested in going out together, we're going to a lab.